You're checking out online. You click the pay button. The page spins for a few seconds longer than usual. You wait. Nothing seems to happen. You wonder if it worked. You click again. 2 charges appear on your bank statement. Or you hit send on a message. It shows as sending, but the status never changes to delivered. You hit send again. Both messages arrive. These experiences feel like bugs. Sometimes they are. But often, the root cause isn't careless programming or a broken server. It's something inherent to how data delivery works across a network. The mechanism is retransmission. The problem is duplication. And understanding why they're linked reveals one of the deepest challenges in networked systems. Cast your mind back to how reliable delivery works. When a sender transmits data, it waits for an acknowledgement from the receiver. If the acknowledgement doesn't arrive within a certain time, the sender assumes the data was lost and retransmits it. This is duplicate delivery. And notice the critical detail. Nothing went wrong in any dramatic sense. The original packet arrived correctly. The acknowledgement was lost, a normal, everyday network event. The retransmission was the right response to that loss. Every component behaved as designed. This is the core of TCP's reliability guarantee, and it's what ensures data isn't silently dropped without the sender knowing. The duplication is not a malfunction. It's an inherent consequence of how acknowledgement-based reliability works, when the acknowledgement itself can be lost. You might think this is easy to solve. The receiver could simply check whether it already received this data and ignore the duplicate. Problem solved. In simple cases, this works. TCP itself handles exactly this situation. When a retransmitted segment arrives, TCP's sequence numbers allow the receiver to recognize it as a duplicate and discard it. The application sitting on top of TCP never sees the duplicate. It's handled transparently, invisibly, at the transport layer. But now consider what happens at a higher level, in the application itself or between services in a distributed system. An application sends a request to a server. Process this payment. The server receives the request, processes the payment, and sends back a response, done. But the response gets lost. The application, seeing no confirmation, retries, sends the same request again. The server receives it, doesn't know whether it already processed this specific request, and processes it again. 2 payments. TCP guaranteed that the bytes of the request arrived correctly. It said nothing about whether the action those bytes represent should happen once or twice. TCP operates at the level of data delivery. It has no concept of what the data means, what action it triggers, or whether that action has already happened. This is the boundary at which TCP's duplicate protection ends and a new, harder problem begins. Below that boundary, in the network, at the transport layer, duplicates are handled. Above it, in the application logic, in the business semantics of what requests mean, duplicates become the application's problem to solve. And solving them correctly is genuinely difficult. The difficulty has a name in distributed systems: the problem of exactly once delivery. Exactly once delivery means that a message or operation is processed exactly 1 time, not 0 times, not 2 times, exactly once. It sounds like a basic requirement. It turns out to be one of the hardest guarantees to achieve in a distributed system. Here's why. For exactly once delivery to work, you need 2 things simultaneously. The sender needs to know the operation happened so it doesn't retry unnecessarily, and the receiver needs to ensure it processes the operation only once, even if it receives it multiple times. Both of these requirements are hard to satisfy together, especially when the network can lose messages at any point. If the sender doesn't retry when it doesn't get a response, you risk at most once delivery. The operation either happens once or not at all. Sometimes that's fine. If you're sending a non-critical notification, losing it occasionally is acceptable. But if you're processing a payment, at most once means some payments might silently never happen. If the sender retries aggressively whenever it doesn't get a confirmation, you risk at least once delivery. The operation definitely happens, but might happen more than once. For a file download, this is harmless. For a payment, it's a serious problem. Exactly once sits between these two. You want the operation to definitely happen, ruling out at most once. You want it to happen only once, ruling out at least once. Achieving both simultaneously, in the presence of a network that can lose any message at any time, requires deliberate design. The standard solution is a concept called idempotency. And it's worth understanding clearly because it's one of the most important ideas in building reliable distributed systems. An operation is idempotent if performing it multiple times produces the same result as performing it once. The classic mathematical example is multiplication by 1, 5 times 1 equals 5, and 5 times 1 times 1 still equals 5. Doing it again doesn't change the outcome. In software systems, making operations idempotent means designing them so that receiving the same request twice has the same effect as receiving it once. The key technique is the idempotency key, a unique identifier attached to every request. When the server receives a request, it first checks whether it has already processed a request with this identifier. If yes, it returns the result from the first processing without doing anything again. If no, it processes the request, stores the result alongside the identifier, and returns the result. Now the sender can retry freely. If the first attempt succeeds and the response gets lost, the sender retries with the same idempotency key. The server recognizes it, returns the stored result, and the operation has effectively happened exactly once, from the application's perspective, regardless of how many times the request traveled across the network. This is how payment systems at companies like Stripe work. Every payment request carries a unique idempotency key. The client can safely retry any request after a timeout, after a network error, without fear of charging a customer twice. The idempotency key ensures the payment happens once, and once only. But idempotency isn't free. It requires the server to store state, a record of every processed request identifier, for long enough that retried requests can be recognized. That storage has to be durable. If the server crashes and loses its record, it might process the same request again after restarting. It has to be consulted atomically. If 2 copies of the same request arrive simultaneously, the server has to handle them without processing both. These requirements add complexity, cost, and potential failure points. For every system that says we guarantee exactly once processing, there's significant engineering underneath making that promise real. And sometimes, even with careful design, duplicates get through. A system that doesn't store idempotency keys long enough might process a retry that arrives after the key expired. A system that checks for duplicates after the first processing rather than before might handle 2 simultaneous requests before either has been recorded. The corner cases in distributed systems are genuinely hard. Duplicate delivery is a window into a fundamental truth about distributed systems. You cannot have certainty in the presence of failure. When a sender transmits a message and doesn't receive a response, it faces irreducible uncertainty. Did the message arrive and the response was lost, or did the message not arrive at all? There is no way to distinguish these 2 cases without additional information that the network cannot provide. The retransmission that causes duplication is the rational response to that uncertainty. When you don't know whether something arrived, you send it again. Not retrying risks losing the operation entirely. So you retry and accept that sometimes the receiver gets it twice. Idempotency is how you make twice harmless. It doesn't eliminate the duplicate delivery. The duplicate still arrives. It makes the system's response to the duplicate identical to the response to the first delivery. The duplicate is neutralized not by preventing it, but by making it not matter. This is a recurring pattern in distributed systems design. You can't eliminate the hard problems the network creates, but you can design systems that are robust in the face of them. Duplication happens. Build your system so that duplication is harmless. The next time you accidentally submit something twice and only one action occurs, that's idempotency at work. That's not accidental. It's engineering.